This law of radicals focused on nested radicals, which is talking about an expression where our index is too large but can be factored by m and n, and we have the same radicand here. Because we cannot simplify this with too large index, we can actually just transform it in this manner where the same radicand can either be simplified using one of the factors of our index n or even m itself. Again, this law or rule is covering the idea that this is too large, but a factor of our index can simplify our radicand here. So we simply need to look for the factors of that and break it into this manner. But of course, you're going to show its validity. A here is again our radicand, while m and n would be our indices. Okay. So we are going to show that from here, this is equal to that and also equal to this one here. So let's start with this expression. Again, already given that our index may be too large but can be factored by either m and n. Just like, say for example, if it's 50, so we can factor it as 25 times 2. Right? That's just like that. Now, if we have something like this, take note that we have that transformation of a radical expression into an expression with fractional exponent. Take note that this has an exponent of 1. That would mean we can rewrite this as a to the power of a fractional exponent where the exponent of 1 becomes your numerator, and this mn is actually your denominator, m and n. Okay, so just like that. This is a transformation from a radical expression into an expression with fractional exponent. Now from here, you can separate, okay, the exponents as a product of two different fractions. You can have it a times 1 over m, raised to the power 1 over m times 1 over n. Because if this will be multiplied, 1 times 1 is just 1, m times n is just m n. From here, take note that our expression here is using the concept of the power law of exponents. And when do we get product of exponents? That is when we have an exponentiation already expressed to another exponentiation. This time, if we are going to take these two, you will have a to the power of 1 over m, which is already raised to another exponent of 1 to the power of n. So this, we have this loss of exponents. So this is just a product of exponents now. Now returning to an expression with radical expression with m as our divisor here or denominator, it becomes your index. So you have the mth root of a to the power of 1. This is still raised to 1 over n. Okay? So removing this 1 here, you have your mth root of a, still raised to the 1 over n. Let me move up here. So what happens then now? This entire expression is also raised to another fractional exponent. So we can write another radical expression. We're treating this now as our new radicand. This would become the nth root, as this is our denominator, of the expression mth root of a raised to 1 as the numerator here. So basically it looks like this, the nth root of the mth root of a. So this shows the second statement here. Okay, the second statement here, which tells us that if we have again index that is too large but can be factorable by m and n, you can separate that into this nested radicals. We call this nested radicals. But we have shown the second. How about the first? This can be drawn from here because this is under multiplication, and multiplication is commutative. This can be written as a to the power of 1 over n and 1 over m. Following the same pattern here, this will become a to the power of 1 over n using power law of exponents. Then, transforming this first, you have the nth root of a to the power of 1, which is still raised to 1 to the power of m. So that 1 will be will not be written anymore. Now, we'll be treating this as whole, and now subjecting that into another fractional exponent. So this becomes the mth root of this entire expression becomes our radicand with exponent 1. Basically, it ends up here, nth root of a. So we have shown the two statements for nested radicals rule. Again, the point of this is we have an index that is too large or maybe large, but it has a factor where we could simplify our a here. Because what if this is a perfect square and m is a factor of mn is even? So we can simplify that. But we can simplify that just by sticking to this one here. So this shows this law. This again another video for properties, laws, and theorems. Please subscribe now.